Given that y is equal to 5 over x plus 6 cube root of x, find dy by dx when x is equal to 8. dy by dx means the differentiation. The first thing we need to do is get every term to be x to the power of something. That is the right format if we want to differentiate. Now the first term is 5 over x, and that means 5 over x to the power of 1. So if I bring the power up to the top, it becomes 5x to the power of minus 1. The second term, 6 cube root of x. Cube root of x is the same as x to the power of a third. So I can write that as 6x to the power of a third. If I just leave the question for a second and look at this green box on the left-hand side, we're going to consider the general formats for differentiation. Y is equal to x to the power of n. The differentiation of this, we would bring the power to the front, so it becomes nx, and we would decrease the power by 1, so it would become n minus 1. That is a general format for differentiation. So back to the question, if I want to work out dy by dx, the differentiation of y with respect to x, the first term, we're going to bring the minus 1 to the front, so it's going to be multiplied by minus 5, and we're going to decrease the power by 1, so it becomes minus 2. The second term, the power comes to the front, so a third multiplied by the 6, and if we decrease the power by 1, a third minus 1 is minus 2/3. If we simplify this, minus 1 times 5 is minus 5. So the first term becomes minus 5x power of minus 2. The second term, a third multiplied by 6 is 6/3. I can write that as 6 over 3. And if we simplify that 6 over 3, of course, 6 divided by 3 is equal to 2. So my differentiation is minus 5x power of minus 2 plus 2x power of minus 2/3. That is the differentiation, but it is worth noting that we could write this out as well without the negative powers. So that's what I'm going to do next. Minus 5x power of minus 2 is the same as minus 5 over x squared. And the second term is the same as 2 over x to the power of 2/3. Now, focusing on that second term, in the denominator you've got x to the power of 2/3. What you can do there is split that up to be x to the power of a third squared. And of course, x to the power of a third is the same as the cube root of x. So I'm going to write it as like this. And I'm going to write it back up here so I can carry on with this question. Now it's worth noting that on Unit 1 you are allowed a calculator. However, it's worth thinking this through in a non-calculator way so that you can then consider if your answer in the end actually makes sense and you've shown your workings out. So if I'm looking at this one, it does actually say in the question to find dy by dx when x is equal to 8. So I need to substitute x equals 8 into the question, into the differentiation. What this means is for every x I've got, I need to swap it to be 8. So if I'm looking at the formula for the differentiation, so dy by dx is equal, instead of minus 5 over x squared, I'm going to write down minus 5 over 8 squared. And the second term becomes 2 over cube root of 8 squared. 8 squared is 64, so I've got minus 5 over 64, and cube root of 8 is 2, so I've got 2 over 2 squared. And 2 squared, of course, is equal to 4. At any point here, we can just type this on a calculator, but I'm just thinking this through and showing what you would do without a calculator. So for this one, the denominators would need to be the same if I want to add fractions together. So if I multiply the top and bottom of the second fraction by 16, it would give me 64 as the denominator, which would match up with the first fraction. The differentiation, therefore, is 27 over 64. What we could do, of course, is type that in your calculator at any point, and you could just write the decimal equivalent, which would be 0.421875. Integration. This is asking us to find integration of 5x to the power of 3 over 2 plus 12x power of minus 5 plus 7. Now to integrate, remember that integration is the reverse process of differentiation. So this time, if we have a look at the general formats, first of all, we're going to increase the power by 1, so it becomes x to the power of n plus 1. and we're going to divide by that power. So we're going to divide by n plus 1. If I just leave that for a second and have a look at the bottom here, we have 3 examples here of differentiation. I've got y equals 2x cubed, y equals 2x cubed minus 7, and y equals 2x cubed plus 13. If we differentiate the first example, it gives us 6x squared. Now what that means is if I integrate 6x squared, it should give me 2x cubed, which it does. However, if I look at the second example, that also gives me a differentiation of 6x squared, as does the third one. What that means then is that if we integrate 6x squared, it could be 2x cubed, but it could also be 2x cubed plus or minus any constant really. For example, it could have been a minus 7, or it could have been a plus 13, it could have been a minus 100. So what we do when we integrate, to represent that constant, we have to make sure we put a plus c at the end. This can also be written, instead of dividing by n plus 1, just be aware that some people will write that as 1 over n plus 1 multiplied by x to the power of n plus 1. Let's have a look at the question again. To integrate, similar to differentiation, we want every term to be x to the power of something, which they are. So if we have a look at the first term, we have 5x to the power of 3 over 2. So we need to increase 3 over 2 by 1. So that becomes 5 over 2. Then we need to divide by that power. We need to divide by 5 over 2. If we have a look at the second term, we need to increase the power by 1. So increase minus 5 by 1, it becomes minus 4. And then we need to divide by the minus 4. If you have a look at the third term is a plus 7, it's a constant. So remember, any constant can be thought of as 7x to the power of 0, because x to the power of 0 is equal to 1. If I increase that power now by 1, it becomes 1. And we divide by that power, so we divide by 1. And of course we need to remember that possibility of having a constant at the end, so we put the plus c in. So that's my integration, but we should simplify this. If I look at the first term again, we have 5 over 5 over 2. So you could just type that in your calculator. If you want to think about it in a non-calculator way, just remember that 5 divided by 5 over 2 is the same as bringing the 2 up to the top to become 10 over 5, which would give us 2x power of 5 over 2. As I said, you can just type that in on your calculator. Second term, you have 12 divided by minus 4. 12 divided by minus 4 is minus 3. The second term becomes minus 3x power of minus 4. Third term, you have 7 over 1. 7 divided by 1, which is 7. So we write down 7x. And we still ensure that we put the plus c at the end. So that's my integration. So that's my answer. If you have the time and want to double check your answer, what you can do is work back and differentiate. And we should, if this is right, we should get what was in the question as an answer. So if I write down y is equal to my current answer, and what I'm going to do is I'm going to differentiate them. So this time we're going to bring the power to the front, so it becomes 5 over 2 times 2, and we're going to decrease the power by 1. So 5 over 2, take away 1, would leave us with 3 over 2. The second term, the minus 4, comes to the front, so minus 4 times the 3, and we decrease the power by 1, so the power becomes minus 5. And then the third term, the 1 comes to the front, so 1 times 7, and we decrease the power by 1, and it becomes 0. And of course, the differentiation of any constant is 0, so I don't need to put anything after that. If I tidy this up now, if I just simplify, we have 5 over 2 times 2, which becomes 5. And the second term, we have minus 4 times 3, which is minus 12. And then because it's minus 12, it would become a plus 12. And we have 1 times 7, which is 7. And then, of course, because you've got x to the power of 0, anything to the power of 0 is equal to 1. So it's just a plus 7. If I compare that to what was in the question, I can see that I'm right, that it does actually match up. So we know that we're right. It's worth also adding a couple of tips for you. Any constants, when you integrate, you may have already noticed this, but if you integrate any constants, then you just need to put the x after it. So for example, integration of 7 is 7x, integration of 9 is 9x, integration of minus 13 is minus 13x. And then if you differentiate any constants, just remember that that is always 0. Now, to go over what differentiation actually is, let's look at a very simple common example. So I'm going to look at y equals x squared. If we first of all have a look at a sketch of the graph of y equals x squared, we can have a look at what the gradients would be at different points on this curve. So for example, when x is equal to 2, I would have to draw a tangent to that curve at that particular point. So what that means is drawing a straight line that touches the curve when x is equal to 2. Now at GCSE level, that is all you would have to do. You'd have to draw a tangent at a particular point, and you would then work out the gradient of that line, and that would give you the gradient of the curve at that point. The problem is that can be very difficult to get accurate. So what we can do is link this with differentiation. So if I just have a look at a couple more examples, so when x is equal to 1, if I draw a tangent to the curve at that point, I can see that the line, the tangent, is not as steep as the first one. When x is equal to 0, we would be drawing a horizontal line, which would mean the gradient of the tangent would be 0. So let's go back to the curve. So y equals x squared. If I differentiate, that gives me 2x. So to link this with the gradient, the tangent, what you need to remember is that the differentiation gives you a formula for the gradient of the curve at any point, which means that you've now got a formula for the gradient of the tangent at any point on that curve. So for example, when x is equal to 0, if I want to know what the gradient of the curve when x is equal to 0, I just need to substitute that value into the differentiation. So instead of dy by dx equals 2x, I can now write down 2 times 0, which gives me 0. So the gradient of the curve is 0 when x is equal to 0, which means the gradient of the tangent to the curve is 0 when x is equal to 0. If x is equal to 1, and I want to work out the gradient, so what I can do is use the differentiation again and substitute 1 in. So instead of 2x, 2 times 1, which gives me 2. So the gradient of the curve when x is equal to 1 is equal to 2, which means the gradient of the tangent to the curve when x is equal to 1 is 2. And similar, I can look at x is equal to 2. The gradient when x is equal to 2 would be 4, and then when x is equal to minus 2, the gradient would be minus 4. So if you need to work out the gradient of a curve, just remember that differentiation can help you with this. In the same way, if you need to work out the gradient of a tangent, for example, if the question's asking you to work out the equation of a tangent, you may need to first of all work out the gradient of that particular tangent. So again, if you know the equation of the curve, then you can differentiate to get a formula for the gradient.
It's a good idea to think about why it is that when we differentiate a constant, whether it's on its own or involved with a function, it just gives us 0. So for example, if we had y equals x squared plus 3, then when we differentiate, we get 2x plus nothing. We don't tend to bother writing that. Why does it give nothing to the gradient? Well, the thing is that what this is telling us actually is that y equals x squared plus anything when differentiated gives us 2x. And one way to think about this is graphically. If we draw an x squared curve, then the plus k just means that it is lifted up or down. So we can think of it as y equals f of x plus k. And what the k in that case always does is moves a function up or down. Up if it's positive, down if it's negative. So if we just draw x squared itself, and there's our axes. So in black, it's minus x squared. Then if we draw a gradient, so say here, then the gradient is going to look like that. So that's the gradient at that point. Now, if we instead want to look at x squared plus 3, what that will actually do is move the x-axis down to there. So this point here is now 3, but the gradient hasn't changed. And if we wanted to look at x squared minus 2, let's say, then if that were our x-axis, that's the same as the curve having moved down by 2, but the gradient at the relevant point where the green tangent meets the curve is still unchanged. So moving a graph up and down doesn't change the gradient at any point, which is why when we differentiate a constant, because the constant just represents moving the graph up or down, then it doesn't contribute anything to the gradient. This question refers to the fact that differentiation and integration are related, and in fact are opposites or inverses of each other. And you already know something about this, although said in a different way, from knowing about velocity and distance and how they're related. So if we have a velocity time graph, then if we draw it, then you already know that the distance is given by the area under the graph. So that would be x, the distance, and you now know that the integral is the area under the graph. Now you also know that if we have a distance time graph, then if you want to find the velocity, then say we want the velocity at this time here, then we would draw a tangent, and the gradient of the tangent will give us the velocity. Now the gradient of the tangent is the gradient of the curve at that point, so this is telling us that dx by dt, which tells us the gradient at a point, is velocity. And so from this we can see that, at least in this situation, the integral and the derivative go in opposite ways. If we want to go from x to get v, we would differentiate, but if we want to go from v to get x, we would integrate. Now, that's a good indication that these are opposites, but we still don't know for sure that it's true. So what we can look at is looking at the area under a curve and see if we can get anything from that. So say we want to look at the area of this curve from here to here, then if we were going to increase that area by a little bit, so we add a slice on, and this is going to be a little slice, so delta stands for little, so that's a little added area. Now if we put on that this is the x value and that we're just adding a little bit, so the width of this slice here is delta x, we can also say that the height of it, so the height there will be y, and then we'll get a little change in y, so we'll get y plus delta y. So what's the area of this little delta A? So delta A is roughly equal to the width of this rectangle, which is delta x, times by the height of it, which is roughly y. If we then divide by delta x and swap it round, we get that y is roughly equal to delta a over delta x. And then, as we did when we were differentiating from first principles, we can take a limit of this as delta x tends to 0, and that gives us dA by dx. So what do we now know? Well, we know that what we mean by the integral of the function y is equal to a. But we also know that dA by dx is equal to y. And so, just as before, we can say that if we want to get from a to the function, then we differentiate, and if we want to get from the function to a, the area, we integrate. So whilst this is not a rigorous proof, it does at least show us that it's reasonable for us to work along the lines of integration and differentiation being opposites.